Hi, I'm Dr. Courtney. Thanks for joining us today at Carmel Academy, where our goal is to teach you to do science like a boss. And how do I know that you can do science like a boss? Because God says so. In the Bible, in Psalm 8, David writes under the guidance of the Holy Spirit, "O Lord, our Lord, how majestic is your name in all the earth. When I consider your heavens, the work of your fingers, what is man that you are mindful of him, the Son of Man that you care for him?" And then he answers, also under the inspiration of the Holy Spirit, "For you made him, mankind, a little lower than the heavenly beings, and crowned him with glory and honor to rule over your creation, over the beasts of the field, the birds of the air, and everything that swims through the seas." So we know, because God says so, that we can do science like a boss. Okay, so the experiment today is the way the ball bounces. So the basic idea is that we're going to drop a golf ball, let it bounce off a hard surface, and you need to find something fairly hard for this, like a granite countertop or a concrete paved floor, something really firm. The bench top here in the laboratory is wood. It's not really big and massive and firm enough to work, so I just have the ruler set up here as an example. When we really make the videos we're going to use to test our hypothesis, will be set up down so we're actually bouncing the ball directly off the concrete floor, and the ruler that we're using as a length scale is also sitting on the concrete floor. But let's talk about our hypothesis a little bit, because the experiment needs to be designed to test the hypothesis. So the hypothesis is simple. It's that the bounce height is proportional to the drop height. In other words, if we drop it from, say, 50 centimeters high and it bounces up to 40 centimeters high, right, in that case, the proportion is 40 divided by 50, or 0.8. So if that's the result of dropping it from, say, 50 centimeters high, then if we drop it by 40 centimeters high, then the bounce from 40 centimeters high would be 80% of 40, or 32 centimeters, and so on. So expressed as an equation, if we call the bounce height HF for final, so that would be the height that it returns to after a bounce. So the equation would be H final equals some constant K times H initial. So H initial is the drop height, H final is the bounce height, and this K is the constant of proportionality. So the way we're thinking about this, if we were to draw a little picture here, here's H initial, drop it, it comes down, bounces off the floor, and comes back up to some H final. And when we say it's a proportionality, this K is a constant of proportionality, so it's the same, according to our hypothesis, our prediction, for every bounce. So then if the next initial height was the same as the final height for the first one, it would be like this. And one of the convenient ways of doing this experiment, and one of the advantages of doing it on video, is that if you find a really flat spot on the concrete or a real level spot on a granite countertop, you can get it to bounce multiple times. So when we analyze the video, the final height of our first bounce can be the initial height of our second bounce. So we only have to drop the ball once, and if we can record 5 to 7 bounces, we can complete the analysis and the experiment in a small number of drops. And I like golf balls. This is a nice orange one, shows up well in the video. Okay, before we import the video into Tracker and do the analysis there, I like to just watch the video on an ordinary media player in Windows to see what we have. So here goes. Okay, so what we see is we see the ball being dropped from approximately 50 centimeters high and bouncing 5 or 6 times, and the video seems to catch most of it reasonably well. We have the camera rotated so that it's in portrait mode, so you get more pixels along the direction of motion, which enhances accuracy a little bit, because the way this camera works is that there's almost 2,000 pixels in the long direction and only about 1,000 pixels in the short direction. So we're really more interested in the vertical motion, so we tilt the camera sideways so that there's more pixels. And in some media players, and we'll see in a minute in Tracker, one needs to rotate the video back because it's going to appear sideways originally in the video. So a couple other features to be aware of is that the camera placement is as close as possible to the same level as the action or the middle of the action, because there is some vertical motion. So the camera is looking straight on into the event rather than looking down or looking from the side. The camera placement being straight on is rather important. We've also prepared a notebook table for the analysis, just with one column for the sample number, one column for the initial height, and one column for the final height. Okay, so far all we've done is open the video in the Tracker program, and let's show you how to rotate it. If you go to the video menu, select filters, we want to apply a new filter, and we want to rotate. And you can see that if we rotate counterclockwise by 90 degrees, that will give us what we want, so the ball's bouncing up and down rather than side to side. We've also sort of moved the video forward in the player to the point of the motion that we're interested in. And so now we need to do a couple things that we almost always do in Tracker. One is to click this here, which helps us set up a coordinate system. And we want our 0 in height to be at the bottom of the meter stick there. And we don't want it just to be close, we want it to be pretty accurate, so we can zoom in. And so I zoomed to full 100% of the original size to more accurately place our coordinate system. The left right doesn't matter so much, but we really want the 0 in height to correspond to the bottom of the meter stick, and there we go. Now we also want to place a scale of some sort, and this helps the Tracker program convert pixels to the unit of height or measurement, which is in this case going to be centimeters. So we want to create the calibration tool, we create a new one, and we create a calibration stick. And so it says shift click to mark end 1, so we're going to mark end 1 at the bottom, and we're going to create this at the bottom of the meter stick. So shift click there gives us 1 point, and you can see a little blue square, and then we're going up to the 50 centimeter mark here to shift click and to place the other calibration point there. So now we've created our 2 calibration points, and so now we need to enter the length in units for that calibration stick. So it just sort of defaults to length. I think it probably counted pixels there, but one ends at 0, one ends at 50 centimeters. So the length of our calibration stick is 50 centimeters. Put that in there. And it says change the length unit to centimeters. Yes, that's what we want to do. So now it knows that our calibration stick is 50 centimeters long, and now we can zoom out for a more appropriate perspective. And as we walk through the video, we'll be zooming in and out between 25% zoom, which lets us see the whole thing, and 400% zoom, which allows us to see what's happening with a little greater accuracy as we record the relevant heights in our notebook. So let's go ahead and play it because we want to catch the height of the ball right before it's dropped. I'm an imperfect experimenter. My hand's moving a little bit in there, so we want to catch it right before the drop. Okay, so we went a little too far there, so we back up frame by frame to try and catch that frame right as or right before it's dropped, so that the fingers are off of it there, so it's already on the way down. The fingers appear to be touching it there. Fingers appear to be touching it there. So it's still holding on there, so maybe go forward 2 frames. And if you want to know, gee whiz, what frame am I on? Because sometimes things don't seem to be moving at all. The frame number right here, and this is frame 1860. So as you frame through, and this button moves you 1 frame forward, this button moves you 1 frame back, you can see the frame number change. So if your eye's not detecting any motion, because the hand's just holding the ball right there, you look at the frame number. So let's go ahead and zoom way in on frame 1860. I'll zoom in by 400%, and let's find the ball. And there's always a choice one makes whether or not to use an edge of an object for the position or whether or not to use the center of the object. And in this case, we're going to choose to use the bottom edge of the ball for our position. And why is that? Well, it's the bottom edge that's going to hit the floor. So when the bottom edge hits the floor, that's 0 height. So to know how high the ball is above the floor, rather than use the center of mass, we're going to use the bottom edge in this case. So if you just move the cursor over to the bottom edge within a pixel, it displays the X and Y positions of the ball right over here in yellow. And so the Y position of the ball, which is the initial height for the first bounce, it's 50.32 centimeters, so I record that in the lab notebook. Alright, now if we play it, it's not going to make much sense now, so let's go ahead and zoom out to 25% to try and catch the height on the first bounce. Alright, so now we're close to the height on the first bounce, and it seems like I might have stopped it when it's still going up. So go forward 1 frame, forward 1 frame. Okay, between those 2 frames it came back down, so back up 1 frame. So that's the maximum height right there. So go ahead and zoom in to 400%. Find it again by panning over to the meter stick and then panning up to the ball. And so this is the final height for the first bounce, and it looks like it's about there. So looking at the yellow box right there, tells us that the final height is 42.35 centimeters. Now, since we're just letting the ball bounce several times in this case, the final height for the first bounce is also the initial height for the second bounce. So I am entering into the lab notebook both the final height for the first bounce as well as the initial height for the second bounce as 42.35. And so now we can go ahead and zoom out so we can see what's happening and let it forward for it to bounce again and trying to catch it at the top. Okay, So we stopped it near the top, and we'll go forward a frame, still moving up. Oh, moving back down there, so let's back it up one frame. So that's the top of the motion as near as we can determine. And so I think the golf ball's to the right of the meter stick a little bit. Oh, there it is. So let's go ahead and determine its height to be 35.78 is where the cursor is right now. So we write that in our lab notebook, 35.78. And now the final height for that bounce is also the initial height for the next bounce. So this is what we record in our lab notebook. And let's go ahead and zoom back out to 25% so we can follow the bounce. And let me make the comment here that the ball is moving a little bit left to right, and in a perfect world we would have had a more level concrete slab, but we tried different places around the laboratory, and this was the best we can do. As long as the ball is moving left to right and stays the same distance from the camera, that left to right motion is not introducing much error at all. However, if the ball moves toward the camera or away from the camera, that introduces a lot of error, and you really want to retry the experiment and get a video where the ball is a constant distance from the camera, which also, well, that's the way to do it accurately. Alright, so let's go ahead and move forward for the next bounce. Alright, so that's close to the top. Forward one. Okay, that moved down, so we back it up a frame to get the frame where it's close to the top. And then let's go ahead and zoom in. And we can see the ball right there. Pan over to the ball. And then put the cursor right there at the bottom edge of the ball. And now it's at a height of 30.26 centimeters. So the final height for bounce 3 is 30.26, and that's also the initial height for bounce 4. And let's go ahead and zoom back out to 25% and get the next bounce. Alright, move forward a frame, going down, so move backward a frame. Backward a frame. So move one, that's the highest, the peak height as far as that we have caught on a given frame. Zoom in to 400%, pan over a little bit, pan down a little bit, move the cursor to the bottom edge of the ball. And you can see that there's a little bit of a blur, and this happens the way the interleaving works on the camera because the ball's not perfectly still. But we want the highest point of the ball, so when we've got this pixelation effect happening because there's a little motion, I try and put the cursor at the smooth edge of the ball because it's between frames and there's a little motion, and I want the highest point of the lower edge so it's closer to there than it is to there. So 25.77 is the final height for the fourth bounce, which is also the initial height for the fifth bounce. Alright, zoom out. Go ahead and play it. Alright, and that's close to the height for the next bounce, and it's headed down if we go forward a frame, go back a frame, go back a frame. So we want to go forward a frame. So that's the highest point right there. I'll go ahead, zoom in to 400%, pan over. The ball by this point is near the right edge of the frame. And there it is. So the bottom edge of the ball is at 21.99 centimeters. So we got 5 good bounces in the video, and then it moved off to the right of the screen, so that's good enough to move forward. So we have all our data now in our lab notes. Alright, so here we are in our spreadsheet. We put some header information, golf ball, drop, bounce drop experiment, named the kind of camcorder that we used. The drop height was approximately 50 centimeters, and we set up our columns much like our lab notebook with some extra columns in there and some extra rows for the analysis. So we're just inputting our data straight out of the lab notebook, 50.32, and so the final height was 42.35. And rather than double enter, I almost always double check and I copy and paste. Haven't done this for a while. Copying and pasting a number once you've entered it one time properly reduces data entry errors in spreadsheet. And there's a couple of ways that you can analyze this. One way is just to compute the ratio of every bounce, because the hypothesis was that there would be this direct proportionality, and the prediction of a direct proportionality is that this ratio would be the same every time. So in the spreadsheet formula, just to compute the ratio, it's the ratio of the final height to the initial height, and here the final height is in element C6 and the initial height is in element B6. So the formula would be equal C6 over B6. And so we can see that the ratio is 0.84, or about 84%. So the prediction of our hypothesis would be that these other ratios would be about the same, or exactly the same. So we're going to cut and paste the formula just to, so this is going to put it in, that's C7 over B7, C8 over B8, and so on. So what we see when we compute all the ratios is that they're all between 84 and a smidge over 85%. So the ratio of the bounce heights is rather close to constants within a percent or so. So now we can also come down here and we can compute the average with the spreadsheet formula, equal average, and so we're averaging the numbers in this column. So this is the average between D6 and D10. So the average is, as we'd expect, all the numbers are pretty close. So 84.74% or 0.8474. And I like to compute the standard error, which is a nice metric of the uncertainty for these things. So that's STDEV, and then the square root of the count. Hang on, gotta be a little more careful about this. STDEV, D6 to D10, D6 colon D10, and then divided by the square root SQRT of the count, D6 colon D10. So the standard error is an estimate of the uncertainty. So the uncertainty in the mean is 0.022, which is less than 1%. It's about 0.2%. So now we enter the Linus formula to compute a least square fit. So equals Linus. And the dependent variable is C6 to C10, because it's the final heights. So enter like that, and then a comma, and then the independent variable is B6 to B10, and then we enter a 0 to tell it to do a proportionality going through the origin, because we know if you drop a ball from 0 height, you're not going to get any bounce. The final height's also going to be 0. And then 1 tells it to output the statistics, and then hitting Shift, Control, Enter gives us the whole array of output rather than simply the slope. So we get the slope is 0.8455. The y-intercept is 0 because we set it to be that. The uncertainty in the slope is 0.002, and the r squared tells us is 1, and it's probably not exactly 1, it's just 1 to some number of significant digits. And one can also compute what's called a COR, or a coefficient of restitution. And what the coefficient of restitution is it's the square root of the slope in this case. And I'm including this not because it's critical from the physical science point of view of this experiment, but if you happen to be doing this experiment in an 11th or 12th grade physics class rather than an 8th or 9th grade physical science class, you might want to talk about energy considerations and how much energy is lost in the bounce, and also compute this common physics number called the coefficient of restitution, and that's simply the square root of the slope in this case. So it's the square root of element B13. So the coefficient of restitution of this golf ball is 0.92, so one could look up online and compare that with other experiments that have been done measuring the coefficient of restitution of a golf ball. And let me also mention that if one is using this laboratory for a 11th or 12th grade physics class rather than a 8th or 9th grade physical science class, that one may want to repeat this kind of analysis for 3 or 4 different drops of the golf ball, taken 3 or 4 different videos to confirm that you get very nearly the same result with multiple trials rather than a single trial. Alright, and as a final step, let's go ahead and get a graphical look at this. So we'll open up our Graph.exe program and we'll insert the point series, and let's just call it ball drop. I want to get a little more specific. I'll call it golf ball drop. And if we do a zoom fit, it'll bring it into view so we can see our data points. And let's just take a little more care with our axes here. Our x-axis, let's go from 0 to about 60, and let's label that axis properly as the initial height, and make sure we include the units of centimeters. And let's go ahead and have it auto tick and auto grid, because usually it makes good choices. And the y-axis, let's also run from 0 to 60, and let's label it properly as the final height. Oh, we forgot to put our units on the y-axis, so it's the final height in units of centimeters. Alright, so our graph is looking pretty good. We can go ahead and have it do a least square fit here also. If you right click on the data, insert the trend line, select a linear trend line, make the intercept 0. Let's not make the color pink, let's make the color blue. There you go. We can see that a line goes through the origin. The coefficient is 0.8455, same as it was in Excel, and that the r-squared value is very close to 1. Alright, now that we've done the experiment on the way the ball bounces, and hopefully you'll do the experiment at home, and we've demonstrated the analysis, let's talk a little bit about how I want you to think when you're writing the discussion section of your lab report. And hopefully your parents, your teacher, whoever's supervising your science class is going to have you writing lab reports. So you always want to circle back around in your discussion and address the issue of whether or not your hypothesis is supported. And remember, our hypothesis was that the bounce height would be proportional to the drop height. And there's always fine print in that. What did we hold constant? So we're holding constant the surface that we drop it on, we're holding constant the type of the ball, but what we're varying, right, the independent variable in this experiment is the drop height, and then the dependent variable is the bounce height. So the hypothesis was that the dependent variable, the bounce height, would be proportional to the independent variable, the drop height. All right, and then how well is it supported? Since this is a high school science class, we usually want to say something more quantitative than simply the hypothesis was supported. How well? Was it supported within 20%, 10%, 5%, or 1%? Because the hypothesis that's supported within 1% is supported much more strongly than one that may only be supported with an accuracy of 10%. So we try and do a good, accurate experiment, which is one of the advantages of Tracker. And then once we determine whether or not the hypothesis is supported, we also want to, in our discussion section, we want to write down quantitatively how well our hypothesis was supported. So thanks for joining us today at Carmel Academy. I'm Dr. Courtney.